Hey everyone, welcome back to Chem Story. Today we're going to explore an important topic, resolving racemic mixtures. You probably remember that enantiomers are non-superimposable mirror images. Since a lot of synthesis reactions produce racemic mixtures, separating enantiomers becomes really important, especially in pharmaceuticals and beyond. So how do we go about resolving these racemic mixtures? Let's find out. First, let's start by defining what a racemic mixture is. Basically, a racemic mixture has equal amounts of two enantiomers, which are non-superimposable mirror images of each other. That's the key point to remember. Enantiomers have pretty much the same physical and chemical properties, like boiling point, solubility, and polarity. The one big difference? How they interact with plane polarized light. That's where things get interesting. Since enantiomers rotate plane polarized light in opposite directions, but by the same amount, they end up canceling each other out. So when you have a racemic mixture, it's optically inactive, meaning there's no net optical rotation. Even though enantiomers share a lot of similarities, their biological activities can be totally different. In the world of pharmaceuticals, one enantiomer might do its job effectively, while the other could be completely inactive or even harmful. That's why resolving racemic mixtures is such a big deal, especially when it comes to drug development. The enantiomeric purity really matters for both safety and effectiveness. Racemic mixtures often form naturally during chemical reactions. That's because enantiomeric compounds tend to form in equal amounts, unless we use a chiral catalyst or environment to steer the reaction. A classic example is when HBr adds to an alkene. This reaction usually results in a racemic mixture because the key intermediate, the carbocation ion, is planar. Here's how it works. When an alkene reacts with HBr, the pi electrons attack the proton H+, forming a carbocation ion at the more stable position. This carbocation ion is sp2 hybridized and planar, with an empty p orbital sticking out perpendicularly. Since the bromide ion Br- can approach from either side with equal probability, you get a 1-to-1 mixture of R and S enantiomers. Now that we've got a handle on racemic mixtures, let's talk about why separating them is so important. In chiral synthesis, having pure enantiomers is key for stereoselective reactions and asymmetric synthesis. A lot of reactions need a single enantiomer to get the right outcome, especially when designing drugs or creating specialized materials. When it comes to biology and medicine, chirality really matters because biological systems are inherently chiral. Think of it like trying to put the wrong hand into a glove. It just doesn't fit. Enzymes, receptors, and proteins can tell the difference between enantiomers. One enantiomer might bind perfectly, while the other one might not, or even worse, could cause unexpected effects. This becomes especially important in the pharmaceutical world. A lot of drugs show enantioselective effects, meaning one enantiomer works better or is safer than the other. A famous and tragic example is thalidomide. One enantiomer acted as a sedative, while the other caused severe birth defects. That's why, in modern drug development, scientists put a lot of effort into producing and testing pure enantiomers. It's all about making sure the drug is both safe and effective. All right, now let's dive into how we actually separate racemic mixtures. Normally, we separate compounds by differences in things like polarity, boiling point, or solubility. But here's the problem. Those methods just don't work for enantiomers. Since enantiomers have nearly identical physical and chemical properties, conventional separation techniques fall short. To actually separate them, we need some special techniques that bring chirality into the mix. One way to do this is by using a chiral resolving agent, also called a chiral probe. What it does is temporarily convert enantiomers into diastereomers, and here's the key. Unlike enantiomers, diastereomers actually have different physical properties. That means we can separate them using techniques like recrystallization. Once we've separated the diastereomers, we just remove the chiral probe, and we're left with the pure RNS enantiomers. This method is super useful, especially in pharmaceuticals and fine chemical synthesis, where high enantiomeric purity is a must. Let's break it down with an example. Say we start with a racemic mixture of carboxylic acids. That means we've got equal amounts of the R and S enantiomers. Since these enantiomers share the same physical properties, we can't just use conventional methods to separate them. So here's what we do. We introduce a chiral amine as a resolving agent, basically a chiral probe. This amine reacts with both enantiomers through an acid-base reaction, forming diastereomeric salts. Unlike enantiomers, diastereomers actually have different physical properties, like solubility. That's what makes it possible to separate them using recrystallization. It's a simple but effective way to tell them apart. Once we've separated the diastereomers, the final step is to get rid of the chiral resolving agent. We do this by adding an acid, which breaks down the salt and releases the pure R and S enantiomers. That way, we end up with the pure enantiomers, successfully resolving the racemic mixture. This method is really popular in pharmaceuticals and fine chemical synthesis, where high enantiomeric purity is a must. By using a chiral resolving agent, we can efficiently separate enantiomers and get high-purity compounds for further use. Another great way to separate racemic mixtures is through chiral chromatography. In this method, we use a chromatography column where the stationary phase is coated with a chiral substance. This setup creates a chiral environment that interacts differently with each enantiomer. Here's how it works. When the racemic mixture flows through the column, the two enantiomers experience different levels of interaction with the chiral stationary phase. One enantiomer has stronger interactions, so it moves more slowly, while the other one elutes faster. This difference in how long they take to come out shows up as distinct peaks on the chromatogram, making separation pretty straightforward. Let's take a closer look at an example. Here, the R form interacts more strongly with the stationary phase, so it spends more time in the column before coming out. Meanwhile, the S form has weaker interactions, so it exits the column first. By comparing the retention times, we can isolate enantiomerically pure compounds, which is super useful for research and pharmaceutical applications. All right, to sum it all up, racemic mixtures contain equal amounts of two enantiomers and are optically inactive. Since enantiomers have the same physical properties, conventional separation methods just don't work. That's why we use specialized techniques like chiral resolving agents and chiral chromatography to separate them. This is especially important in the pharmaceutical world, where enantiomeric purity can make all the difference in a drug's effectiveness and safety. That's it for today's lesson. Thanks for watching, and I'll see you in the next video.